So welcome everybody to the day seminar. It is a pleasure to introduce the speaker of the day, who is Selim Ghazouani from the Université d'Orsay, who will speak about an invitation to dilation surfaces. So the audience is yours. Thank you.
Okay, thank you very much for the introduction and for the invitation. It's a pleasure to talk to you at your seminar. Okay. Okay, so today so I understand that this is a dynamical system seminar, and this is more going to be a talk of geometry applied to dynamics. So I hope I don't know, you can cling on to the dynamical system bits when the geometry maybe okay. So I'll go. So just to give a bit of context. So yeah, okay. So how could Alessandra, actually, do you think I can
tell me?
Not have, I mean, I don't know, it's disturbing me a bit, all the music of people coming into the room. Okay, no.
Yes, actually I can, but they should stop in a few.
Okay, no problem. I'll try and do without that. Okay, so or maybe I can try and put my headphones on. Yeah, maybe it'll help. Okay, so yes, so this basically I've just drawn like just as a taster and to give a bit of context about what I'm going to talk about today. On one side, the dynamical objects that will be, you know, some of the objects of interest and some of the keywords that you will see from the dynamical part of my talk. And on the other side, some more geometric stuff. So if you've seen some of those words, maybe you'll find the talk of interest, or maybe you can, I don't know, at least relate to some bits of it. Okay, so just if you, so the title of the talk is Dilation Surfaces. So if you don't know any geometry, it won't get any more complicated than pictures of polygons in the plane. So this is just maybe to reassure you if you're not a geometer. And okay, so now let me move to some dynamics to ask some questions. Okay, so the general theme so I'm going to build on today is the following. So you start with got a phase space. That's going to be, let's say, a compact manifold. So we're very quickly going to restrict ourselves to dimension 1 or 2. And we take a family of dynamical systems. And I'm very quickly going to give examples. So just phi p, and phi p are just, let's say, diffeomorphisms of X. And there's a parameter space that I call P here. Maybe it's a manifold itself. It's something where, you know, I can count things. Maybe it's just a 0, 1, the interval. Okay, and I want to ask the question, when I take, you know, the typical element in this family, if I pick P at random, what kind of dynamical behavior do I observe for phi p? Okay, so this is I don't know, it's a question of interest when you do physics, right? So maybe, you know, you're working with you know, abstract dynamical systems, but in practice, when you take some physics law and like see the dynamical system that it generates, almost always you're going to observe some sort of behaviors, and you can maybe discount some things that are just very exceptional. So that's why we want to understand these kind of things. Okay, and to formalize this question of what is this notion of what is typical, there are in general traditionally two competing notions. One that is topological. So if you have a dense G delta set of parameters for which a property is true, let's say, for instance, being minimal or being ergodic with respect to a certain measure, or uniquely ergodic, or whatever, then you say that this property is generic if it holds for a dense G delta set of parameters. And there is another one that's more probabilistic when you say that something is generic if it holds for a full measure set in parameter space. Okay, so today, essentially, we're more going to focus on the second notion. I think it would be reasonable to argue that the second notion is the one that makes more sense from a physical point of view, but maybe I don't want to get entangled in these kind of debates today. Okay, so now let's take a very concrete example. So I'm starting with, let's say, what could be arguably considered the simplest family of dynamical systems. I just take rotations. X maps to X plus alpha on the circle. Okay, so in this family, it's very easy. We can describe everything. So to make things a bit more spicy, I just add a small perturbation that depends on an epsilon. And so I add epsilon plus epsilon times the simplest non-constant periodic function that I know, the sign. Okay. And so I can ask, I've got two parameters for this family. What kind of behavior do I observe? Okay, so this is the question. So what's the generic behavior? It's a question that it's simple, easy to formulate. Okay, so first, I need to tell you what could, at least at the theoretical level, happen. So probably most of the audience knows about the rotation number. That's a theory for circle homeomorphism that essentially tells you almost everything you might want to know about the dynamics of a circle map, but let me remind you of it. So you've got essentially two cases, either periodic orbits. I mean, either your map has periodic orbits, and those periodic orbits drive essentially the dynamics of all other orbits, in the sense that if you take a point, you start iterating your map, then it's going to go and accumulate onto a periodic orbit. Or your map is minimal. And these two cases, so minimal, maybe recall, it means that every orbit is dense. And yes, so this dichotomy corresponds to whether the rotation number, if you know what the rotation number is rational or irrational. Okay. So this problem was initially studied by Arnold, and what he did, he made the following observation. So start from 0. So maybe I can draw a little something here. So nice technology. So if I take, this is my parameter space. So I've got alpha, the rotation parameter, and epsilon here, the size of the perturbation, epsilon times sine of something. Okay. And I look at what happens along that line. So where basically alpha is equal to 0, and I just move epsilon. So here I'm just looking at x maps to x plus epsilon sine. So now you know that, so maybe I call this map phi epsilon. And you notice that phi epsilon of 0 is equal to 0, right? It's just because the sine of 0 is equal to 0. And if I compute the derivative of a phi epsilon as 0, what I get is essentially 1 plus epsilon. Epsilon's then the derivative of sine, which is the cosine at 0, which is equal to 1. So maybe I've got a 2 pi that will have come out when I do this. Okay, but the upshot of this calculation is that if epsilon is well, that's a bit annoying. Okay, if epsilon is less than, okay, but I could consider epsilon negative here. It'll make my life easier. If I take, but everything is going to work for epsilon positive. It's just easier to formulate. The derivative at 0, okay, is less than 1. Okay, and what does this tell you? Well, it tells you that 0, at least locally, is an attracting fixed point. I don't know why I said locally. I mean, there's 0 is an attracting fixed point. Well, it means that at least nearby orbits are all accumulate to 0. So now if I take there is for all x close enough, iterated orbits of x tends to 0. Okay. So this is very nice. And so that essentially tells me that if I go along this line, well, I have periodic orbits. If you like the rotation number, those periodic orbits, they're all of order 1, meaning that the rotation number is equal to 0. And an important feature of attracting fixed points is that they're stable. If you do a little perturbation, then they're stable. They stay there. Okay, so if I go up and I go a bit on the left or on the right, I mean, I see something with width and I see some open set essentially. Okay, so and then what I'm claiming is that you can iterate this reasoning and do it at every rational point. And maybe to do this, you replace phi epsilon by phi to the power of to the order of the periodic orbit. Okay, and so what you're going to see is a lot of little things like that, little tongues, that's what Arnold called them, that are widening as epsilon increases. Okay, and so you see, since rational numbers are dense in the interval, then you're going to see many such little tongues. And if you pushed a bit the reasoning, I mean, if you looked at the picture for long enough, I think you'd convince yourself that the union of those tongues, it's dense in total space. And this is essentially because rational numbers are dense. You need to make sure that you can't have too much in between those, but it's not too different. Okay, so I don't know. Is this clear? Does anybody have a question? I'm very happy to answer at this point. This is supposed to be rather elementary, but so it's a good, I don't know, schematic picture of what's going to happen today. So, okay, I'll keep going then. So the question at this point is, okay, so I've got this set is open, maybe dense. So now going back to my family, having this picture in mind, I know that there are a lot of parameters when I pick, right, there are a lot of parameters for which I'm in option number 1. Okay, and the surprising theorem that Arnold proved is that okay, sorry, so I've forgotten that I wanted to give some formal definition before I tell you about Arnold's theorem. So basically, this case where I've got an attracting periodic orbit, I'm going to call it Morse-Male or asymptotically periodic. I mean, these are a standard terminology in dynamical systems. You probably know it very well. Okay, so, and yes, so this is when, okay, the alpha or omega limit of any point is a periodic point. It's an attracting or repelling one. Okay, so I hope this definition is that it's okay. And the very surprising theorem that Arnold proved is that even though this subset of Morse-Male things is open and dense, its complement still has positive measure. So if you pick such a point at random, there is still a possibility that it's going to be minimal in spite of its complement. The complement of minimal things having is being open and dense. Okay, so if you look in parameter space at the space of alpha epsilon of irrational rotation numbers, such they are minimal, you can see that if you take slices, epsilon is equal to constant, what you're going to see as a counter set is that you would build by removing some open slices here every time you see a rational number. And so what this theorem essentially tells you is that those counter sets, well, despite being counter set, they still have positive measure. From this point of view, maybe it's a bit less surprising. We know that there are counter sets of positive measure, but still. Okay, so that's Arnold's theorem. Okay, and actually this theorem is actually a bit more general if you take parameter family of circle diffeomorphisms, class Z infinity, infinity, provided the rotation number varies along this family, then the set of parameters such that the corresponding diffeomorphism is minimal will always have positive Lebesgue measure. Okay. And somehow, and it's probably what I want to discuss today, the case of circle diffeomorphisms is very special in the realm of one-dimensional dynamics. And this would be for reasons, essentially because for circle diffeomorphisms, KM theory applies. And you have like KM-like phenomena that you won't see in general. Okay, so this is just to be for the people who like KM theory. Okay, so just to keep toying with these kind of objects, I'm just going to take something slightly different. I'm going to take a map of the interval, a bijection of the interval, this whose graph I've drawn, and it's a piecewise continuous affine map. That is the bijection. So I'm going to call that an affine interval exchange map, just because I think of the continuity interval of this map being permutated and permuted, and so yes. So, and I can say, okay, now I can take this map. It's one map, and I can turn it into a one parameter family, and I'm going to do that in the simplest way I know. I'm just going to add a parameter. So I take this map and I conjugate it by a family of rotation. Okay, so when I do that, I just take mod 1. I'm thinking of this map of the circle, in case that wasn't clear. Okay, and I can ask again, well, what is the dynamical behavior in this family? So here it's just so is that actually how what happened when I started working on these kind of things with my co-authors Charles Fougeron and Adrien Boulanger. I don't know, we came from geometry, we started toying with these kind of things, and so just took the computer and started plotting the attractors. We took, in this family, a parameter alpha, and we take a point x at random, and we iterated the map and saw on what it accumulated, then varied the parameter alpha, and well, you see these kind of cute pictures, and you see a lot of. So I think this is probably the thing I want to get at some point. In this picture, you see a lot of self-similarity. Somehow, what you see here seems to be a zoomed-up version of these guys. A zoomed-up version of this guy. Okay, and hopefully I can explain that. Okay, but that's not a theorem. So here you see things that you should be convinced are more small parameters. Here you've got a periodic orbit of order 1, 2, 3, 4, 5, 6, 7, 8, 9, and other periodic orbits of length that is growing, and you tend to accumulate on things that are very complicated. So clearly you have a very similar picture to the one of the Arnold songs, where you have an open and probably dense, if you are able to zoom close to those parameters where you can't really see, open and dense set where you have periodic orbits, and you want to know, okay, well, the complement, does it have a positive or zero Lebesgue measure? Okay, so that's the question for today. And so this is a bit of a spoiler, but you can prove, if you do the right thing, that in this particular family, and this is somewhat very different from the case of circle diffeomorphisms, but for almost every parameter, you have, well, your map is more small. Dynamics is driven by a few periodic orbits. Okay, and so this set of exceptional parameters that we could see on this plot here has zero Lebesgue measure. And so this is a conjecture that at this point, I think is widely open, and I'm not sure we're anywhere close to a solution. You could conjecture that if you take the parameter space of affine interval exchange maps, that would be those maps that are piecewise. So maybe you fix a number of interval, and you take a map that has this many interval of continuity, and that is piecewise affine bijection. So this is the space of such things as finite dimensional manifold. I mean, you have sort of finitely many parameters, maybe the length and the slopes of the branches. So you have a natural Lebesgue measure, and if you take, with respect to this natural structure, you pick something at random with respect to the Lebesgue measure, and you will always see something that is more space. This is the conjecture. So supported by many numerical experiments, because okay, when you start drawing these kind of pictures, you can actually start computing the size of the domains where you see periodic orbits, and you can, I don't know, okay, make educated guesses. We'll never, you know, be able to say with certainty with the computer what the answer to this question is, but I mean, we've got good reasons to think that this is the case. Okay, this conjecture is true. Okay, so there we go. So okay, so this was the introductory part to explain the dynamical context in which I'm going to develop all those geometric things. And so, okay, two things that we want to take from this. Okay, the question for today is generic behavior in families of dynamical systems. And you've got, so this is really in this particular case of one-dimensional dynamics, sort of invertible, that wouldn't be the case in general, of course. You've got really this competition between minimal and more small, and you can't really get things that are essentially more complicated. You don't have, I don't know, annals of diffeomorphisms or whatever, because you only have one direction and things are invertible. So you can't create expansion in an artificial way. So, okay. So now I'm going to move to the geometry part of this talk and try to introduce the stars of the show today. So, okay. Let me try and give a formal definition first. Actually, a few formal definitions of the things that. So feel free to interrupt me. I really don't know what the background in geometry, the general background of geometry of the audience is. So I don't know, things, I'm just going too fast. I'm very happy to give some more precision. So a dilation surface, what I'm going to call a dilation surface, is a space that you get. You take a nice Euclidean polygon as the one on this picture. And you pair together sides that are parallel, probably not necessarily same length, but parallel. Okay, so not every polygon can be turned into a dilation surface. You need to have sufficiently many pairs of parallel sides. But if you have that, you just do this. And if I do that, so I've got a gluing pattern here, I can see a sort of a fundamental domain. And when I do my identification, I look at the quotient space. And this, in the particular case, you get a genus 2 dilation surface. Okay. So this is a very informal definition. You couldn't really get a proper mathematical object from this. So let me give you a more formal definition. Which is in spirit really not equivalent, because the other one is not a real definition, but which formalizes this construction. The dilation surface is a surface with a particular set of charts. I mean, atlas of charts whose transition maps are affine, and not only affine, I mean complex affine, and whose real, I mean linear parts. The multiplication part is real. Okay, so this amounts to the hypothesis of size being parallel, the fact that you're multiplying by real stuff. Okay, and a set of singularities. So I'm going to go back to my initial picture. When I draw this picture and I do my identifications, somehow I can glue along the sides. I can glue them along maps of this form. Okay, so it's not too complicated to see where the special atlas is going to come from. So there's only one or a few points that can cause problem are the vertices of the polygon, where if you're careful. So one thing that you could check is that all the vertices in the quotient surface are identified to the same point. So when I go around these points, I will see a total angle that is not 2 pi, but actually 6 pi. Okay, and at this point, the structure cannot really be extended. So you have, in the definition, you have to include a finite set of singularities, and to make for a nice theory, you have to ask that the structure, those singularities are not too degenerate. So it's essentially what I said. You need to ask that it's a cone type singularity. So it's almost regular, apart from the fact that the angle that you see when you go around the point is multiple of pi instead of being multiple of 2 pi instead of being pi.
Selim, can I
Yes.
interrupt for a second?
Of course, of course.
So if you go back to the previous slide, so I guess what you're trying to say when you say they're glued, I mean, they are glued affinely. For instance, I'm thinking of the 2 red parallel sides.
Exactly. So you take.
And you can never, and I guess your conditions, the formal definition implies that you can never flip them, if you see what I mean.
Yes. Okay. So sorry, you're right.
Is that right?
This is
Because I mean,
right.
there are lots of ways to glue them, right? So you want to specify.
So if you glue them along affine maps, and when I say affine, I mean complex affine.
Yeah.
You've got only 2 ways. You've got the way where you don't change the orientation, and the way where you change your orientation, where you flip them, say.
Oh, you can flip them.
So but I've asked here that the map which I'm gluing. So okay, I've been a bit too fast on that, but they're real and they're positive. Sorry, I didn't say that. They're real and they're positive, and therefore you cannot flip them.
Okay, that's one. Okay, thank you.
Okay. No problem. Thank you. That's a very, very good question. Okay, I mean, you could do a theory where you flip them. I mean, you could extend the definition, and you would get
then you put the word pseudo in front of it, right?
Maybe half, I think, if you want to be coherent with the. So these things, for those who know, they're the generalization of translation surfaces. So I think people call those translation surfaces where you glue with things where you can change the orientation. They call them half translation surfaces.
All right.
I think.
Thank you.
Yeah. Okay. So, but you could do that. It's just a matter of how general you want your theory to be. That wouldn't make too much of a difference. Okay. So that being said, okay. So I don't know, just another picture of a dilation surface where you can do a lot. So I just wanted to highlight the fact that you can even get tori, dilation tori, which is harder to do when you're working with Euclidean metrics. So again, if you were to merge at the topological level, you could merge red and blue, and you would see that they form only one side. So you really see that you've got a square where you've glued together opposite sides, right? So again, get some of that. Okay, and now, so it's I'm not sure it's a good definition for this audience, but let's say you really like algebraic geometry. Another way to see dilation surfaces, and so it's really not going to be used or relevant to this talk, so you can immediately forget about it. But if that helps to have another way to think of it, it's this definition. This first definition and a half is equivalent to taking a Riemann surface and taking holomorphic differential instead of taking value in the complex numbers, which take value in a flat line bundle over this Riemann surface with an extra condition on the monoidal. Okay, and when you integrate this holomorphic differential, then you get the special charts that are given by the second definition. Okay, so now let's move on to the reason why these are going to be interesting from a dynamical point of view. So if you take any angle, then you start drawing the directional foliation in the complex plane. So again, I really want to think of these things in terms of polygons, right? So if there is a problem that it doesn't, I don't always go back to the formal definition to define things. I'm very happy to give you an equivalent definition in the language of this definition, which is the good one at a formal level. But I think most people are pleased with the pictures and intuitive definition. So I take a direction, I draw the line foliation of the complex plane, And because I'm gluing my sides along parallel sides, what I'm essentially claiming is that this foliation passes to the quotient on my surface. Okay, and, well, this is a fancy way to say that if I take a line, I'm in my polygon, I hit the sides, I don't really know how to continue it. Well, this side is glued to this side, and this point is glued to this point, so I continue it from the point to which it's glued to in the same direction, and I keep going on, so I get a foliation. And there's one such foliation for every angle. So so one oriented foliation, if you take an angle, if you take the opposite angle, so if you take theta plus pi, you get the same foliation, but with a different orientation. Okay. So that's nice. And now if I take a Poincaré map of such a foliation, let's say, for instance, here I could take in the plane a segment here, so I can't really draw here, and I give it its natural parameterization by 0, 1. I look at first return maps of those foliations, and what I will get is piecewise affine maps. I don't know if I need to explain a bit more why I get piecewise affine maps, but that should be pretty clear from the picture, because I'm gluing things along affine maps. Okay. So no question. I can move on.
I think you're fine there.
Yeah, I think I'm fine here. So yes, so I've already mentioned this, but okay. So translation surface has been like quite of a fashionable topic over the past, let's say, few decades. So just for people who already know what those are, it's really a translation surface, which is the case where you restrict the gluing group, where you force the sides to have same length. This is a particular case of translation surfaces. Okay, so sometimes it's helpful to think of those as a generalization. Okay, so now I want to explain to you how to characterize periodic orbits of those foliations in terms of the geometry. Okay, so take the, well, not, yeah, okay. So take the picture that I've used, and you take the segments that whose endpoints are the middle points of the two yellow sides of the polygon. So these guys are glued together, and because they're glued together along an affine map, their middle points via the identification are identified. So now if I were to take the direction that I think I wrongly claimed is theta is equal to pi over 4, I think I got something wrong in my calculation. I suppose if I were to adjust the lengths of green, I could make it pi over 4, but I didn't, so that was a mistake on my part. I'm sorry. And clearly, this the leaf in the direction that is defined by the segment is a periodic orbit, periodic leaf of the foliation. And the other thing that I could convince myself of is that so maybe I'd be better off drawing a little something here. So I don't have yellow in my colors. What does it look like? Got yellow. So how about I replace yellow with, red. Okay, red's okay. Okay, so the thing I want to convince you of is that this periodic orbit is attractive. What's the color? Is black. I'm going to stick with black. So middle point here and middle point here. Okay, good. Okay, and now I'm going to have a look at what happens if I start from this point, say. Start from this point. So this is a closed leaf. Okay, got green here. Okay, so now I take blank. I take the trajectory that's issued from this point. Okay, do you know what? No. I wanted to do. Okay, I'm not happy with this being in black because I want to highlight the fact that it has a this is closed. So in blue, I draw in blue the closed trajectory. Okay, it goes like this, and it's closed. Okay, and now I start, and I take something here that is a distance, let's say epsilon. Okay, and I start. I live my life. So maybe you all see where I want to go. So here I've still got a length epsilon on the picture. Yeah. Okay, so this thing is glued to the point that is going to be a distance epsilon over 2 of this guy, just because the map gluing the red guy to this other red guy is, let's say, shrinks distances by 2. So so this is my first impact point, and it continues here. Ah, no. Okay. And then this is the distance epsilon over 2, and again, it's glued to something that's distance epsilon over 4. Okay, well, okay, long story short, when I take any orbit starting from that point in that direction, I'm going to start accumulating, because the distance in sort of visual metric that I have drawn here is shrinking by a half, or by the ratio between these two things, every time I hit the red side. Okay, so what I wanted to say is that here, well, when I see this configuration, I see an attracting periodic orbit. Okay, very good. What I want to explain to you is that this comes from can be, how do I want to say that? This has sort of a geometric reformulation in terms of a geometric building block. So if I look at my map, what I'm going to show is that in my surface, I can see what I call a cylinder, and I'm going to explain to you what a cylinder is. So I need to define that again. So I'm just going to, sorry, that's. Good. So what is a cylinder? So assume I'm in the complex plane. There I am. So this would be my point 0. Okay. And now I draw an angular sector like this of angle, say, theta. So this is really a picture in the complex plane. And here, I take 2 parallel lines. So these 2 blue lines are parallel, and I glue them together. Okay. So the quotient space of this thing. So I take the quotient space of the trapezoid, I think that's what you call it, that is contained within those blue and red lines. Okay, and this is topologically a cylinder. Okay, and if I look at the dynamics, if I take any direction in this angular sector, if I draw the line that goes through 0. So here I'm like just sweeping out the whole angular sector by lines. Okay, these are closed leaves. The reason why they're closed leaves is because the affine map that maps blue to blue here is centered at 0. Okay, so if you take any line going through 0, it's invariant under the identification. Which means that those pass through the quotient in the cylinder to a closed leaf. I don't know how obvious this is. I think when you play with Euclidean geometry every day, this is fairly obvious. But I don't know. I've played with these too much to know what's obvious and what requires thinking. Anyway, so going to assume that this was clear. And now if I were to take, let's say, any other line, so let's say I consider the rightmost red thing, and now I consider so this is going to be a bit crowded now, but let's say any other trajectory, BIM, well, I see exactly the same phenomenon that I saw earlier, right? I start from this, so I'm in the direction of this guy, okay? Ignore the other green bits. I start in a distance, let's say epsilon here, and here I'm contracted, like when the image of that point here is a point that is closer. I don't really know where, but it's closer. Okay, because this case is fixed. And so again, so you see that all the trajectories in that cylinder that are in the same direction in direction that is comprised within this angular sector, that is defined by the two red things, you see a periodic orbit. Okay, so what's the upshot of this discussion again is that when I see those cylinders, so because in my surface here, if I draw the line that goes from the extremal points of the yellow things, I can see a cylinder embedded in my surface. It gives me a family of periodic orbits. I've explained to you how they are, and they're all sweeping the angular sector that corresponds to the cylinder. And furthermore, those periodic orbits, they're attracting, okay? They're attracting because of the little reasoning that I explained to you. So whenever you've got a trajectory that enters the cylinder, then it's trapped, okay? And so the fact that when you have one closed leaf, you have an entire family of such leaf when you sweep out the angular sector, it's a geometric manifestation of the reasoning that I was explaining to you, that when you have an attracting periodic orbit, when it's stable, so essentially when I'm changing the direction, I'm moving my foliation within a space of dynamical systems, and somehow this is just a remnant of the stability of attracting periodic orbits. One nice thing is that in this geometric world, the domain on which you have such periodic orbits is specified by an angle and by a geometric object, which is a cylinder like this. Okay, so...
Can I just ask a quick question? So you said that these orbits are stable, but they are stable, for example, in this case, in the yellow cylinder, if you go from left to right, but in the red, I expect them to be unstable, right? Because you're expanding the...
Okay, so so you get, this is a little exercise. So when you have an expanding, so it's something I sort of ignored, but it's not too hard to answer your question. So they're also stable, just because when you have an expanding direction, if you take either, so if you have, you know, repelling periodic orbits, or you just take the inverse.
Okay, yes.
And the inverse is also contracting, so it's also stable.
Okay, so in the future or in the past, of course, yes. But...
yes, but I mean that gives you the stability, which is important.
Okay, thanks.
So in general, the only periodic orbits that are not going to be stable are those for which the derivative near to that periodic orbit at that the periodic point or a first return map is equal to 1.
If I may,
yes.
If I may say, I think maybe the confusion here is stability under moving of the initial data and stability under changing the dynamical system or the foliation.
Oh, yes, okay, I see what you mean. Okay, is that, yeah, sorry, Claudio. So, yes, okay, in that case, you're perfectly right. You're perfectly right. So there are two things. I was answering probably the wrong question. I was saying it's stable in the space. And of course, at the level of the fixed foliation, the trajectories in the red cylinder, they act as repellers or sources, right? All trajectories that are near the periodic orbit, they escape and they go somewhere else. Thank you. Okay, thank you very much for this intervention. We're talking at cross purposes. Yeah, that's right. But thank you. Actually, I'm very glad that we stopped to discuss this further, because this is really in the picture, the important picture. No more questions? Okay, good. So I'll keep going. I'll keep going. So, okay, so the interest of having reformulating things like this is that you can tell a lot of periodic foliations of periodic directions just by looking at a picture. Okay, and I'd be tempted to say, and this is really the philosophy behind things, is that if this surface had an extra set of symmetries through, for instance, a big affine isometric groups, then everything that you see with your eye, you could propagate it using, I don't know, symmetries. And that will eventually lead to significant results in the dynamical world. Okay, so this is more for the philosophy, okay? But what I want you to remember is that these things, those cylinders, they act like traps, and they're responsible for those more small foliations. Okay, so this is just on the way, a little question that I think we don't know the answer to yet, even though we've been making a bit of progress on this question with co-authors recently. So does every dilation surface have a cylinder? And does every dilation surface, so this is an extra question, that is not a translation surface, has an attracting cylinder like this? And this, yeah, it's known only in genus 2. I think. Okay. So let's go back to dynamics. Let's go back to that to that family of maps that I suggested you consider earlier, which is you take this affine interval exchange map, and let me tell you how somehow to associate a dilation surface to it. And what I'm saying is that if you take this dilation surface, it's dilation surface of genus 2, let's say you take a horizontal segment going from that side to that side, and you take the first return map of the vertical foliation, the map that you're going to get is this map, okay? And one more thing, so in the problem that I suggested a few slides earlier, I suggested that you consider the family where you take this map and you shift everything by a translation. Well, all this family, you're going to find it in all the directional foliations of this map, and this you can sort of see it because if you take, you know, the directional foliation of angle something, what you will get eventually is a composition of the initial map by shifting everything by something which is going to have something to do with the tangent of the angle that you're working with. Okay. So now I had a problem about parameter families of one-dimensional maps, and I've transformed it into a problem about parameter families of foliations on those dilation surfaces. Okay, well, it's okay. So this is essentially what I was saying here. And essentially the theorem that I had mentioned earlier that you could prove becomes has a more geometric formulation, and it's really going to work. So I told you that in this family almost every direction was Morse male, and this you can transform it in, you take that surface that I obtained like this, and almost every direction theta, you can find a cylinder that is embedded in this surface. So I mean, this surface is identification, so it could be a cylinder that is very crazily embedded in this surface that has a very, very small angle and I don't know, intersect all those sides, I don't know, 1,000 times. Nonetheless, it's still a cylinder, and you're going to have a cylinder embedded in the surface that covers that direction. And this is actually how we prove this theorem. We work hard on the surface to show that it has a big symmetric group, and from what we can see with our bare eye from this picture, plus the shape of the symmetric group, then we get the result. Okay, so I'm not going to say more about this. The last thing I wanted to, so this is just not completely connected to to anything I've said so far. I'm just it's just a good moment for me to define something that is going to be useful in the sequel. I've defined cylinders. When I take a surface, I define an invariance of the surface, which is the largest possible angle for a cylinder that is embedded in sigma. Okay, so you have to show that this is well defined, that you don't have cylinders with angle bigger and bigger and bigger, but this is actually the case, and this defines a function. So maybe there is a chain as well. It's not completely obvious, but you could take a supremum if you didn't like it. Okay. So if you know a bit moduli spaces of I don't know, Riemannian metrics on surfaces, when you have Riemann surfaces, often a good invariant to consider is the length of a closed the shortest length of a closed curve that is not homotopically trivial. It's called the systole, I think, in general. So this is sort of an affine systole, if you like. Another question whose answer to I don't know is does this so okay, so this is probably a question for those who've already seen a translation surface. If you have a translation surface, in particular, you can't have cylinders like I've drawn. You can't have cylinders with there is a notion of cylinders in translation surfaces, but certainly not like that. Certainly not like that, where I take an angular sector and I glue things. The angle of such a cylinder. Sorry, so I haven't defined the angle of a cylinder. Sorry, I mean it's probably quite obvious at this point, but still it's good to say things. So it's the angle here. It's the angle between the two lines in red. Okay. And so these, when you see those configurations, the surface that you get cannot be a translation surface, because when you go about, a closed geodesic, let's say, from the blue thing to the blue thing, you actually need to glue by something that actually shrinks your local charts. Okay, this is a non-Euclidean picture, and there's nothing you can do about it. Okay, again, so this is an aside for those who know what a translation surface is. And so a question is, does this function on the angle characterize as being a translation surface? Open question. Okay. So now I'm just going to accelerate a bit and try to define, okay, formally the parameter spaces that we need. And so I haven't told you where I wanted to end. So I want to explain to you how you can harness all this geometric stuff to prove stuff about dynamical systems, about these foliations. Okay, so now I need to be a bit more formal. So I need to introduce moduli spaces of the surfaces I'm working with, and which are going to those moduli space. So a moduli space of geometric structure is just you take all surfaces, let's say dilation surfaces, you mod out by obvious isometry or isomorphism, let's say, that preserves the affine structure. And you take that, and in general, because those structures are not too complicated, it's a finite dimensional manifold, finite dimensional parameter space. So that's exactly what I do here. I fix the combinatorics somehow. I take my surfaces, I fix the genus is the number of holes in my surface. I fix, so maybe, well, you don't have to, look in detail, but what I mean, but here I fix the number of singular points, the number of points onto which the vertices of the polygon I started with project onto. And maybe I fix the angle around those points. And maybe I fix the amount of dilation that I see when I go around those points. It's essentially the only things that I can fix. And what I get is the moduli spaces of such things where I've prescribed a bit of the combinatorics, say, number of singular points and the angles around them. And this is what I call the moduli space. And this is a finite dimensional manifold. So a way you can convince yourself of that is that, I don't know, this is not, okay, in a very pedestrian way, how many parameters have you to deform this this polygon in C in the complex plane without destroying the dilation structure? Well, you have complex numbers for each of the sides, and you have extra conditions on those complex numbers, so they stay parallel when those that you glue together. So, okay, finite number of parameters. I hope you'll grant me that. Okay, and so now, oh, sorry, I went a bit too far. Yeah, that's where I was. So now you've got this moduli space. You can think of it as the parameter space of my dynamical systems I had at the beginning of the discussion. Okay, and so what I'm saying is that my conjecture, the conjecture that I suggested earlier about almost every affine interval exchange map being Morse-Male, you can rephrase it here by saying you take this moduli space of surfaces, you take points and you only look at the horizontal foliation. And now the conjecture becomes, you can check, it is equivalent. Maybe it's really just a formal game. It's equivalent to saying that for almost every parameter in this moduli space, for almost every surface, the horizontal foliation is Morse. Okay. Just but now I've reformulated questions in terms of those moduli spaces. And now I can sort of, take this this leap and start thinking of, it's a moduli space of geometric structures. So it's not, a dry parameter space where you don't really know what things mean. And it's going to have, some natural geometry. I'm not telling you yet what it is, but, it's not a basic fact of life, but, a basic fact of research in geometry, that moduli spaces of geometric structures, parameter space of geometric structures, often come with a natural geometry which tells you about those geometric structures. Okay, so the one thing, and to define this geometry, you can use the natural invariance, the natural geometry of these things. So, for instance, a few minutes ago, I've defined this this function that's that I've called theta, that goes from the moduli space to the open interval 0 pi. So which spat you out the largest possible angle of a cylinder. Okay, and you can think of this as a function giving you a first approximation of the geometry of D. When you're very close to 0, you resemble a translation surface, at least conjecturally. You don't have, you only have very small cylinders, and on the contrary, when you have at least one big angle of angle pi, well, you have many more Morse-Male directions, because if you look, at least you have almost an angular sector of direction pi in all the possible directional foliation of your surface that has an attracting or repelling closed orbit. Okay, so this is just the kind of things that you start doing. Okay, so now when you have those moduli spaces, and here I'm reusing ideas that have been around for quite a while now to study translation surfaces, you've got a natural action of SL2R on those moduli spaces. Okay, and this action again is the natural action. When you take a polygon in the plane, okay, you take a matrix in SL2R, you let it act on the plane. Okay, you get a new polygon where the sides have been a bit tilted somehow, because SL2R preserves the notion of parallelism. Then if you had two parallel segments, sides of your polygon in at the beginning, then in the image they're still parallel. Okay, SL2R preserves directions in of lines, and so what you get in the end, you can just glue back, and you get a translation surface that's a dilation surface that looks a bit like the original one, but the geometry has changed a bit. Okay, so you've got an action like this. Okay, and for some reasons that I hope are going to become a bit clearer in the. Okay, so I'm running out of time. So, okay, is that okay if I take 5 more minutes to wrap it up?
I would say yes. Take a few minutes to conclude, please.
Okay. So I don't have that much more to say anyway. But so if you restrict this action to the set of diagonal matrices, you get an action that is of interest, and I'm going to try to explain to you why. So this I call the Teichmüller flow. And so this, I claim it is true, and it's not very difficult to check. But what does it do to a dilation surface like this? So look at what it does on the set of directions. It expands the horizontal direction, and it contracts the vertical direction. And what I claim is that if the horizontal foliation has a closed hyperbolic leaf, when I apply my flow, then the trajectory that I get goes to infinity in moduli space. And this is essentially because my closed hyperbolic leaf is going to be contained within a cylinder. And the action on the set of direction is going to open my cylinder. I will start with a cylinder of angle, let's say theta. And as I go along, this angular sector theta is going to become angular sector of angle pi. Okay. And this is essentially the proof of this fact. And if it's minimal, so it's the other case that we can hope. I mean, there are a few other intermediate cases, but I don't want to discuss them today. You can expect some form of recurrence. Or you could even expect that your surface, as you apply this flow, is going to look more and more like a translation surface or other things. But my point is that what's very important is the first point. Okay. And I can tell you essentially how you can hope to prove results is by doing the following thing, by trying to build an analogy between this Teichmüller flow and the geodesic flow acting on this moduli space of dilation surfaces, and the geodesic flow acting on a hyperbolic manifold of infinite volume. So I take 2 minutes to say what I mean by that. I draw a little picture, and then I will be almost finished. So what do I mean by that? What is an infinite volume hyperbolic manifold? So if you take, let's say I'm just going to draw a surface, an infinite volume hyperbolic surface, if you've ever seen one, is something that looks a bit like that. It has like some very thin and finite volume infinite ends that are called cusps, and it has maybe I don't know, we can have as many as you like, but it has things that are called funnels, which are infinite ends of infinite volume that are getting wider and wider. So this is something like that. Okay, and this is a hyperbolic surface, and you take a point to direction, and there is a geodesic, and it lives its life. Okay. And what I'm saying, I mean, at least what I conjecture, is that the Teichmüller flow on this dilation surface things looks pretty much like a geodesic flow on the space like this. And the other thing that I think should be true is that those infinite volume ends, they correspond to places where you have angles. So where the theta function is close to pi, okay, and here is close to 0. And so somehow what I'm trying to prove is that when I start from an arbitrary point in general for almost every trajectory, in the end, it goes and dies in one of those infinite volume ends. Okay, and this by this lemma, so this lemma, if it were to be made, an equivalence, that would give you the fact that almost every element of this moduli space corresponds to a Morse male, at least has a closed hyperbolic leaf in the direction, and then you can start working. So this is how you do this. Okay, so I've just described this, and the reason why you can believe that this analogy would yield anything interesting is because for those hyperbolic manifolds with this nice shape, there is an old theorem of alphas that tells you precisely what you want to know. Those sets of trajectories of the the geodesic flow that end in the wide parts of the surface and die there and never come back. The non-recurrent bits, the wandering bits of the geodesic flow, is a full measure. This is something that be translated in terms of the limit set of the associated group. Okay, so I'm going a bit fast here as the end, and essentially, so okay, I don't have time to say too much, but I think there is a nice dictionary between the two worlds, hyperbolic geometry and dilation surfaces. And so just one thing that I wanted to mention before I finish is that you can actually prove things in using this analogy. At least it's not completely empty in the genus 1 case. When you look at genus 1 with two singular points, there is enough of this analogy that remains true, and you can actually prove the fact that horizontal foliations for two-dimensional, for genus 1 surfaces in general are Moss-Male, almost every. Okay, and this translated back in the world of one-dimensional dynamics tells you that if you take an affine interval exchange transformation with 3 intervals, or a piecewise affine homeomorphisms of the circle, with 2 discontinuities, they're almost always Moss-Male when you pick them at random. Okay, so I think I'm going to stop here. Thank you.
Thanks a lot, Selim. On behalf of the audience, this is silent at the moment. So now it's time for questions. First of all, so. Please, if you want to ask for a question, you just unmute the microphone at the moment.
I have a question, actually. So it's going to be a silly one, if I may. Can I? Okay.
Yes, please.
Okay. In the initial, enucleation of cases that you made, you seem to have skipped over one case, which I believe can happen, meaning the case in which you have a beam of trajectories, the boundary of which could be attracting or repelling, as you see all the time for translation surfaces, which are a subcase of your case. So I suppose that's not generic, probably, in any of the cases that you're interested in.
I'm not sure I understand the case that you're mentioning.
You can have, let's say, an attracting beam of trajectory, meaning you have, I don't know how to describe this, when you're not, you can have minimal components, and you can have components in which you have a beam of trajectories basically with the same needing combinatorics.
So you mean mixed behavior? You have 2 parts of the surface? And...
Yes. Or you can have a beam of trajectories that whose boundaries, you have a boundary on one side and the other side are attracting periodic orbits or repelling periodic orbits. You can have that. For instance, in the, as you know, in the internal wave billiard, in the trapezoid.
So in that case, okay, but unless I express myself badly, I think those cases, even though you're right, there are a few cases that I've voluntarily ignored because they were not generic or because they're essentially mixed behavior. But the one you're mentioning, and I think maybe I haven't been clear enough, you have one attracting and one repelling periodic orbit.
You can have, just imagine the case in which this periodic orbit becomes a beam of periodic orbits that are all...
I see what you mean. You mean when you have... okay.
See what I'm saying?
Yeah, of course. Okay. So that's precisely one of the cases. So let me just draw a picture and you tell me if... okay, well. So you're just saying when you have a rectangle, for instance, you just have this, right? It's a Euclidean rectangle, sort of a limiting case of the trapezoid that I had before. Okay, and now if I look at, vertical trajectories, right? You've got, in the same direction, you've got infinitely many periodic orbits.
that, yeah, this is a simple case because you only have those things, but that situation can happen, within other cases as well. You see what I'm saying?
Of course. So they can happen. So in the end, I think, I hope I'm not, I didn't ever say that those were the only behaviors that you could see.
Oh.
So the reason why I've ignored those is that, as you said, they're not generic.
Okay.
And you don't, I mean, sometimes there are interesting things to say about them, but since in the end, what you want to prove is that actually almost never happens, you can focus on the things you expect are going to happen all the time. But now that you've asked the question, there are actually, many more, slightly more intricate behaviors that can happen. So I essentially said, okay, you've got periodic orbits or you're minimal. And actually, there are sorts of intermediate things where you're neither minimal nor have a periodic orbit, but you have a subsurface. Let's say you're a surface of genus 2, and you've got a surface of genus 1, where all the dynamics happens. And maybe that there you've got sort of Cantor-like attracting sets. And then maybe it acts as an attractor. And maybe in the rest of the surface, you've got a source. Maybe it's a periodic orbit. Maybe it's an attractor of that form. And again, those are not going to be generic. But this is just, okay. This is, yeah.
Okay, no, thank you, though. Thank you.
Thank you. Meanwhile, there are other questions or comments? Okay, I don't see any in the chat, so let me, okay, no, indeed. Let me thank again Selim Ghazouani for the very nice seminar. Again, it was a pleasure.